Hi everyone, welcome back. So in this video, I wanted to talk about the method of stationary phase that we have used twice. Once for range migration of SAR and the other one was for range migration of MIMO radar. Since we've used it before, this is more like an appendix video. You don't really need to know this to apply the algorithms, but just for mathematical completeness, I thought I'll show you how it's done. Okay, so we'll call this method of stationary phase, OSP. So we will use it to solve the 2D Fourier transform of the range migration Green's function. So we saw that there's a Green's function for the um actually I shouldn't say range migration. Let's just say radar Green's function. So you have the radar Green's function. It's of the form either e to the minus jkr over r or 4 pi r. That's the one way. And if you take the two-way Green's function, it is e to the minus 2 jkr over 4 pi r squared. So in the MIMO case, we saw that this was in the MIMO, this showed up in the MIMO RMA, and this showed up in the SAR RMA. Right, so we'll see how to take the Fourier transform of something like this using this method of stationary phase. Okay, so I'll leave a reference in the description. There's a book by Papoulis that discusses this technique. And it generally comes under the category of asymptotic techniques. So I won't cover the proof. You can look at the proof in this book, but it is an elegant proof. Okay, so let's get started. I'll say, okay, we'll start with some intuition behind what this is. So let's say I want to find the integral of some function. The function looks like this, f of x times e to the j phi of x dx. So let's say I want to find this integral, and for argument's sake, I'll say my function looks like this. So I have one part of it is f of x. So let's say it's slowly varying. So let's say this is slow. So it's doing something like this. And then let's say, phi of x can be anything, but this whole exponential term is sinusoidal, right? It has a real part and an imaginary part. So this varies very fast when when phi of x is large, right? So this varying, it could vary something like this, right? So the product of these two functions also is fast, varies very fast. And if we look closely at any region, then the integral over this region basically goes to 0, right? Because the positive part and the negative part kind of cancel each other out. Okay. Another thing to keep in mind is that integrals like this that are very fastly oscillating or oscillate very fast are numerically not very stable. So this would be numerically unstable. Right? What does that mean? That means that if we try to do it using a Riemann sum over xn, f of xn, e to the j, p of xn, then you need to first make sure that the sampling is very high. And the second thing, you need to take I mean, it doesn't converge. This doesn't converge. I mean, you can see that as you take larger and larger values of x, you have to take a lot of values for you to get some reasonable result. So that is an issue. Sorry, my screen recording stopped for a second. Anyway, so it's numerically unstable. So we would like to have some kind of approximation that we can use, or some trick that we can use to compute integrals like this. And that's what this method of stationary phase is. Okay, so what's the intuition? Right, so let's say my phi of x so let's say the phi of x is varying very fast, and then at some point it starts to slow down, and again speeds up. So this slowing down happens when this is actually not phi of x, sorry, this is the real part of e to the j phi of x. Right, so if you take phi of x itself, so if phi of x is increasing, and then it slows, and then it decreases like this, or it is going the other way. Let's say it's doing something like this. So if this is phi of x, or this is phi of x, then you can see that this phase term starts to rapidly oscillate. But here, since it has slowed down, this phase term also slows down. And so I should say actually, this is this, right? So we can see that the contribution to the integral from all of this is mostly 0. But here it's not 0. And here I'm assuming that, x goes from minus infinity to infinity. If there are endpoints to x, let's say it's a finite integral or definite integral between 2 points, to finite points, then even the endpoints will have a contribution, because it doesn't have a region on this side and this side to cancel it out. But we won't consider this case for now. We'll just consider the case where there is a single point where this function slows down. So this is called a stationary phase point. Right, so around this point, this phase starts to become more and more stationary. It's not oscillating wildly. And the idea is that just by observing the behavior around this region, the entire integral can be computed. So the entire integral can be computed just by looking at what the value is in this region. Another way to say that is that it's by looking at what the value is at this region and the the different derivatives of the function at this region. Okay, so let's see how that's done. So hopefully that makes sense. That's the intuitive explanation as to what's going on. So if phi of x has a stationary phase point, that is, when phi prime of x is equal to 0, then that integral can be computed in this neighborhood. Or I should say in the neighborhood of x naught, i.e. X naught is the region, is the solution to phi prime of x equal to 0. Okay, I won't prove this method, like why it works, but hopefully that's intuitive. All right, so let me go back. It's 10.1, so let's say 10.2. So we look at the actual theorem. Okay, so the theorem says integral xy f of x comma y e to the j v of x comma y dx dy is approximately equal to 2 pi j f of x naught y naught divided by square root of phi xx phi yy minus phi xy square times e to the j phi of x naught y naught, where x naught y naught is, I don't know why my screen casting keeps dying. Excuse me for 1 second. Okay. Where is the only singular extremum of phi of x comma y? So that is where, so x naught y naught is the point where d phi dx dx equal to 0 and d phi dy equal to 0. Okay, and then we have to also define some other terms. Phi xx is d square phi dx square at the x naught y naught point. Similarly, phi yy is d phi dy square at x naught y naught. And finally, phi xy is d phi dx dy at x naught y naught. Okay, and then we also have to make sure that f of x comma y is continuous at x naught y naught, and phi xx phi yy minus phi xy square is not equal to 0, and also phi yy should not be equal to 0. Okay, so that's the full statement of the theorem. Okay, so we see that essentially if we know what the value of f is at the stationary phase point and the value of phi is at the stationary phase point, and the second derivative of phi, all the second derivatives of phi at the stationary phase point, then we can evaluate this entire integral, right? So that's pretty amazing. I mean, only at one point, if you know these values, the value and the second derivative of phi and the value of f, then you get a good approximation of the entire integral over the entire xy plane. So that's really the essence of this stationary phase approximation. So let's look at a couple of examples. These are standard examples that show up very often in electromagnetism. So in, for example, Green's functions and scattering problems and imaging even, as we've seen. Okay, so let's take the first example, 10.3, is let's take the one-way free space Green's function. And we want to find the Fourier transform of this. Okay, so what does that mean? I'm trying to say, give me the 2D Fourier transform of e to the minus j k square root of x squared plus y squared plus z naught square over square root of x squared plus y squared plus z naught squared. And you can put a 4 pi in here, it doesn't matter. That's the actual Green's function, but I'll just ignore the 4 pi for now. That's just a constant. Okay, so what is this? So that means that, so the actual integral, explicitly to write it out, is e to the minus jk square root of x squared plus y squared plus z naught square minus j kxx minus j kyy over square root of x squared plus y squared plus z naught square dx dy. And that's the integral we want to compute. Okay, so let's go through, I guess, calculate. And nothing really new now. It's just basic calculus. So we say f of x comma y is square root of x squared plus y squared plus z naught square. And phi of x comma y is minus k square root of x squared plus y squared plus z naught square minus kxx minus kyy. Right, so now that we have this, all we need to do is find these values. So we need to find x naught, y naught. To find x naught, y naught, then we need to evaluate these second derivatives at x naught, y naught, and then plug all those values back in here. So let's do that. I'm not going to do all the steps because, I mean, this is fairly simple to do if you know basic calculus. So I'll just kind of go through it quickly. So phi x, which is the first derivative of phi with respect to x, is minus xk over square root of x squared plus y squared plus z naught square minus kx. Similarly, phi y is minus yk over square root of x squared plus y squared plus z naught square minus ky. So then what you do is you make, we say phi x equal to 0 and phi y equal to 0, set these two, and then find the solutions to the system of equations. And if you do that, you'll see that x naught has two values, plus or minus z naught kx over square root of k square minus kx square minus ky square. And similarly, y naught also has two values, plus or minus z naught ky over square root of kx square, k square minus kx square minus ky square. Now upon substitution, you'll see that only the negative solutions are real. So substituting reveals that only negative solution satisfies phi x equal to phi y equal to 0. Okay, so we found the stationary phase point, and now we find the second derivatives and evaluate it at the stationary phase point. I've already done this, so I'll just give you the final result. K square minus kx square square root of k square minus kx square minus ky square divided by k square z naught. Similarly, phi yy, from symmetry, really, you can say that this is nothing but k square minus ky square square root of k square minus kx square minus ky square over k square z naught. And finally, phi xy at x naught, y naught is equal to minus kx ky square root of k square minus kx square minus ky square over k square z naught. And then evaluating the phase itself at the stationary phase point gives minus z naught square root of k k square minus kx square minus ky square. And f evaluated at x naught, y naught, which is equal to, what was f? 1 over square root of x square plus y square plus z naught square, right? So f at this value is square root of k square minus kx square minus ky square over z naught k. Okay. So then if you evaluate phi xx, phi yy minus phi xy square, that turns out to be k square minus kx square minus ky square over kz naught. So you essentially just take these three results and you put them into this, and that'll give you that. Okay, very nice. So it looks like a lot of terms, but a lot of cancellations take place. And finally, you substitute them back into the original result. Then you get that the 2D Fourier transform is given by 2 pi j e to the minus j z naught square root of k square minus kx square minus ky square over square root of k square minus kx square minus ky square. Okay, you can actually call this kz, which is what we did in the videos. Call this also kz. Then this becomes 2 pi j e to the minus j kz z naught over kz. Okay, so here we found the 2D Fourier transform of a symmetric Green's function, which means that it's symmetric in phi, right? There's no phi dependence that you can see here, so you can write this as rho square and cylindrical polar coordinates, rho square. There's no phi dependence. But what if you have a shifted Green's function? So what do I mean by that? So what if instead of x squared plus y squared, you had x minus x naught squared plus y minus y naught squared plus z minus z naught squared? Well, that's easy. Now you can use just the shifting property of the Fourier transform, and you can essentially just, replace this with some new variable x prime, y prime, z prime. And at the end, you'll add the phase terms. So you'll get an e to the minus j k x x naught minus j k y y naught and minus j k z z naught. Right, so that's just using the shifting property of the Fourier transform. So essentially, we've solved the general Fourier transform result, not the specific case, by doing this. Right, so if I write it out explicitly, it'll be that the Fourier transform of e to the minus j k square root of x minus x naught square, or let's say x minus x prime square, because that's what we've used, plus y minus y prime square plus c square over square root of x minus x prime square plus y minus y prime square plus z square. This is given by 2 pi j e to the minus j kz z naught minus j kx x prime minus j ky y prime divided by kz. Or I can write this as 2 pi j over kz. Okay, so that's the result. So that's the 2D Fourier transform of the free space Green's function. So we can put a 4 pi here, and then you'll just get a 2 here, and this 2 pi will go away. But let's just remove that for now. Okay, so that's a nice result, of course. Can write kz here as square root of k squared minus kx squared minus ky squared. Okay, one thing to keep in mind is that you see that this result at the end has this kz term, which has a singularity, right? So I just want to mention it here that there is a singularity when kz equal to 0, right? So when kx squared plus ky squared is equal to k squared, that's the edge of evanescent modes, you'll see a singularity. So you need to be a bit careful about that. But typically in radar applications that you don't really see that. So we should be fine. But anyways, okay, so that's one of the typical examples that we usually see. I want to treat one more example. So let me just scroll back. Sorry about that. So we call this the one-way space free space Green's function. Be consistent. 10.4. So two-way free space Green's function Fourier transform. Okay, so the two-way case will be double integral xy e to the minus j 2k square root of x squared plus y squared plus z naught squared divided by x squared plus, it's bad looking x squared plus y squared plus z naught squared e to the minus j kxx minus j kyy dx dy. Right, that's the integral we want to find. So here f of x comma y is 1 over x squared plus y squared plus z naught squared. So we saw this was the Green's function for the SAR range migration case. Luckily, the phi of x comma y is the same or very similar, which is just minus 2k square root of x squared plus y squared plus z squared plus k or minus kxx minus kyy. So except for this factor of 2, which can be absorbed into the k, everything else is the same in phi. Of course, f is different, but phi is the same, so it makes my life much easier. I can just say phi of x naught y naught is minus z naught square root of 4k squared minus kx squared minus ky squared, same as last time. And then square root of phi xx phi yy minus phi xy squared is equal to 4k squared minus kx squared minus ky squared over 2k z naught. And we have to recompute f of x, x naught comma y naught, but that's straightforward. I've done it already. It gives you 4k squared minus kx squared minus ky squared over 4k squared z naught squared. Okay, substituting all of this, it gives the Fourier transform to be equal to pi j over kz naught e to the minus j z square root of 4k squared minus kx squared minus ky squared. Okay, so again, you can use the translation properties, spatial translation properties to find the result for when you have a generalized generalized function like x minus x prime square, y minus y prime square, and so on. I can write that out. So 2D Fourier transform of e to the minus 2jk square root of x minus x prime squared plus y minus y prime squared plus z squared z naught squared divided by x minus x prime squared plus y minus y prime squared plus z naught squared. Don't need to put the e over there. This is equal to okay, so yeah, this is equal to pi j over kz naught e to the minus j z naught square root of 4k squared minus kx squared minus ky squared minus jkx x prime minus jky y prime. That's it. Okay, so that's basically the end of it. So we solved the two general cases that show up a lot in electromagnetism, specifically in radar and scattering problems. So this is a very useful result to have. I'll make a quick video about it because we've used these results in the past. Okay, if you have any questions, leave them in the comments below. If not, hopefully that was useful. Thank you and see you in the next one.